Welcome to the workshop. Today we are working on this Fender Blues DeVille. This amplifier was manufactured between 1993 and 1996. I have not determined the exact year of production for this unit. The serial number is located on its 4x10 cabinet, which is currently a few blocks away at the music store. This amplifier is equipped with two 12AX7 preamplifier tubes, one 12AX7 phase splitter tube, and two 6L6 GC power tubes. The rectifier consists of four 1N4006 silicon diodes. For reference, here are the part numbers on the output transformer, the filter choke, and the power transformer. The guys at the store looked this amplifier over before bringing it to me. They got it to function, but only to discover that it sounds terrible. Let's flip it over and take a look inside. It is 1993 and we already have some of the worst design concepts ever incorporated into a tube amplifier design. The tube sockets are mounted directly to a printed circuit board. The traces on this circuit board are not robust enough to supply adequate current to the tubes without heating up and burning out. A majority of the wires are connected using spade connectors. The potentiometers, jacks, and switches are mounted directly to the main circuit board. These ribbon cables, which are used to interface the main circuit board with the tube socket circuit board, are often problematic. The solder pads are too close together, the traces are too thin, and the wires are too thin. These Illinois Capacitor brand electrolytic capacitors are notorious for failing prematurely, but that may not have been a common problem just yet when this particular amplifier was manufactured. Only two electrolytic capacitors have been replaced in this amplifier. After over 30 years, with at least several of those years in service at a rehearsal studio, these electrolytic capacitors have far exceeded their service life. With that said, if this amplifier is going to be put back into commercial service, every electrolytic capacitor within this unit should be replaced. The guys at the music store have already powered this unit up, so I am fairly confident that the electrolytic capacitors are not going to blow up in my face when I switch it on. Let's plug in a speaker cabinet and instrument cable to try it out. The 4x10 speaker model of this amplifier has a 4 ohm and 8 ohm output, but the outputs are not labeled on the chassis. According to the schematic diagram, this white wire is the unused 2 ohm tap. The green with yellow stripe wire is the 4 ohm tap, and the green wire is the 8 ohm tap. This is still quite confusing because these jacks are also switched. Matching the impedance is not critical if we are just testing this out for a few moments at a relatively low volume. The amplifier should be a lot louder. Let's try the other output. Wow, something is really not right. Let's see how it sounds when we plug in a guitar. That is a really dreadful sound. Not only because it sounds terrible, it could be indicative of a major problem. This output is barely functional, and it sounds terrible. Let's start our diagnosis by measuring the voltages going to our plates, the screen grids, and the bias voltage going into the control grids of our power tubes. The voltage being fed to both of our power tube plates is nearly identical. This is a fixed bias amplifier, which means that there is negative DC being fed into the control grids, but there does not appear to be a way to adjust the voltage. The bias voltage is identical going into both control grids. The voltage being fed to both screen grid resistors is identical. There is voltage at the opposite end of both resistors as well. Let's pull out the power tubes and see if we can measure the resistance of the primary winding of the output transformer. We need to unplug the center tap and then measure the resistance from the center tap to both ends of the winding. From there, we measure the resistance of the winding from end to end. The two halves should measure relatively close in resistance, and the reading from end to end should be close to the sum of both halves. We are not taking precise measurements right now. We are simply looking to see if the winding is burned out or shorted internally. Both ends measure relatively close in resistance from the center tap, but they are a bit off. This is most likely not the cause of our problem. The measurement from end to end seems normal. Let's try to measure the secondary winding. I had mentioned earlier that these jacks are switched. Here is a close-up shot of these jacks. This jack seems a bit worn, so I will try to bend it back into place before we proceed. In order to get an accurate reading, we really should disconnect the secondary wires from the circuit. For now, we are going to measure everything in place and just mess around with the switches on the jacks. Again, we are just looking for an open or shorted winding right now. Surprisingly, the readings on our multimeter seem normal. Let's try measuring the current draw from our power tubes. Now we are getting some results. These readings are very strange. Let's plug in a guitar. Let's try a new set of matched 6L6 GC power tubes. These new tubes draw a lot more current, but the problem remains. For good measure, let's plug in a guitar. These new power tubes sound a bit better than the old ones, but they did not solve our problem. Let's see what the output waveform looks like on an oscilloscope. This magnificent oscilloscope was given to me by my friend Denny Allen. Thanks again, Denny. The output should display as a smooth, sinusoidal waveform. In this video presentation, I have given you a wealth of empirical data to process. What is your diagnosis? Please leave a comment below. Thank you very much for watching our video presentation. We currently have a room full of vintage amplifiers lined up to present to you. Please like this video and subscribe to our channel so that you will be notified upon our next release. If you have any amplifiers or instruments that need repair, feel free to give us a call at the store, or you can send us an email.